Good morning, my name is Chris, and I'll be your conference operator today. At this time, I'd like to welcome everyone to the webinar of 3D Visual Measurements conference call. All lines have been placed on mute to prevent any background noise. After the speaker's remarks, there will be a question and answer session. If you'd like to ask a question during this time, simply press star the number 1 on your telephone keypad. If you'd like to withdraw your question, press the pound key. Tom Ward, Senior Product Manager, you may begin your conference, sir.
Well, thank you, and welcome, everyone. I'd like to thank everyone for spending some time with us today to let us share some great technology with you. Before we start, I'd like to introduce my colleague, Clark Bendel. Clark's a principal engineer and the technical product leader for RVI, and I'm Tom Ward. I'm a senior product manager doing new product development for RVI. Clark and I have been combined for over 40 years of learning and sharing experience in the remote visual inspection business. It's been a lot of fun getting to meet people all over the world during that time, and I'm hoping we can share some of that learning with you today. Today's agenda is really quite simple. We'll provide an overview of 3D measurement technologies. They are 3D phase and 3D stereo. Discuss some common measurements and show potential errors that can occur when not using 3D visualization. Share how using a point cloud of 3D data can significantly decrease the potential for error in measurements. And point you to some great resources where you can learn more about video borescopes and 3D measurement technologies. And finally, we'd like to answer any questions that you have as a result of today's discussion. With that, if you have questions during the presentation, please share with Paul Thompson using the chat feature, and we'll grab those and be prepared to answer those at the end of today's call. So, what is the importance of measurement accuracy? Well, we measure to verify asset condition, asset serviceability, some common applications, surface wear, corrosion and erosion pitting, tip clearance, some specific stator rock for gas turbines, and even weld conditions within pipes and tubes. But I'd like you to think about this in a different way as we start. Remote visual inspectors make decisions that put planes back in the air. They make decisions that get gas turbines and wind turbines turned back on and making power. Decisions are made to ensure the weld integrity of oil and gas systems. And if those decisions are incorrect, it can lead to hundreds of thousands of dollars of lost uptime. And worse yet, it can have serious safety implications. As I've traveled around the RVI community within the power, aerospace, and oil and gas business segments, there's usually 3 types of measurement users I speak to. There's remote visual inspectors that are newly encountering measurement application needs, so they're wanting to learn more. There's advanced measurers. They're looking for innovation that make their jobs easier and more efficient. And finally, there's inspectors that use measurement today, but they fall into traps that can create potential inaccurate results. And now I'm going to turn it over to my colleague Clark for a demonstration. But before I do, I want you to consider this. A measurement system will almost always provide an answer, but you need to consider if it's the answer to the question you really wanted to ask. Clark?
All right, thanks, Tom. So let's start out by taking a look at some technologies we can use to perform 3D measurements. So the first is stereo measurement, which has been around in its basic form for well over a decade on video borescopes. So with stereo, we have a tip adapter that provides separate but overlapping left and right image views. The horizontal spacing between common surface points in those 2 images decreases as the tip is moved closer to the surface. So by using software to match these common surface points, we can use this horizontal spacing to calculate 3D surface coordinates for measurement. So here's a stereo image that shows this effect. The cooling holes up here near the top of the screen are further away from the tip, and the horizontal spacing between them is larger than the spacing between the closer cooling holes down toward the bottom of the image. So in first generation stereo systems, the user is positioning these cursors in the left-hand image, and the software tries to identify the same surface locations in the right-hand image, and then it uses that horizontal spacing to compute a 3D coordinate at each cursor location, and then those coordinates are used to calculate the measurement result. So this form of stereo can give you accurate measurements, but when you only have this 2D image to look at, it can be pretty tough to spot potential sources of error. So that brings us to the second generation of stereo measurement, which we launched last summer, and we call 3D stereo. So here, instead of only computing 3D coordinates at the locations of measurement cursors, we apply more advanced processing to compute a full 3D surface map, or point cloud. An on-screen visualization of this 3D point cloud data brings a number of benefits, which we're going to demonstrate to you shortly. So we have 3D stereo available on our 4mm, 6.1mm, and 8.4mm diameter probes. So our second and more advanced 3D technology is called 3D phase measurement, or sometimes 3D PM. So here we have 6.1mm diameter detachable tips that include a patented structured light projection system. So we capture images of a sequence of line patterns projected out from these tips, and then we process those images using a technique called phase shift analysis, which allows us to, again, compute a full 3D point cloud of that viewed surface. Now, 3D phase measurement, unlike stereo, provides a high-quality full-screen image that is great for general inspection while also providing measurement capability on demand. So by eliminating tip changes, we make the inspections more efficient, and you don't have to worry about the problem of relocating an indication after withdrawing the probe to attach a measurement tip. So we find that for most 6.1mm diameter applications, our customers generally prefer to use 3D phase over 3D stereo. So we've introduced two different technologies, 3D stereo and 3D phase, that both give us this 3D point cloud data set. So in this context, that 3D point cloud is a large set of calculated XYZ surface coordinates that are used to compute the measurement results. An on-screen visualization of this 3D point cloud data provides a number of real benefits to the inspector. First, you can better understand the actual contours of the surface you're looking at. You have an ability to assess the quality of the 3D data that's being used to calculate your measurement results. And you can also check the locations of your measurement cursors on the 3D surface where the measurement's actually performed. So it's really hard to overstate the additional information that you get from this 3D point cloud view as compared to a normal 2D image. We have a number of different measurement types that can be used with both 3D stereo and 3D phase, and these can address a broad range of application needs. So these run from simple types like length and point to line to more advanced types like area depth profile and measurement plane, which are new in the upcoming 2.50 software release. So I'm not going to go into a lot of detail on these today, but our 3D measurement handbook describes each of them along with recommended applications and best practices. So that's a really great resource. All right, so now we want to take a look at some images that will show how the use of the point cloud can help you avoid mistakes that are easy to make when you're just looking at a 2D image. So for this, I'm going to be running the Mentor Visual IQ handset software right on my laptop. So what you see on the screen is exactly what you'd see on the handset, except that the operations that I do with the mouse, you would perform using the touch screen on the handset itself. So for our first example, we have a 3D phase image of a surface indication that looks like it might be a dent or a gouge. And we'd like to know the depth of this indication, so we've applied a depth measurement. With the depth measurement, we position 3 cursors on the unaltered portion of the surface to establish a reference plane, and then a 4th cursor down in the indication. And the measured result, which in this case 109 thousandths, is the perpendicular distance between that 4th cursor and the reference plane. So looking at this 2D image, this appears to be a properly performed measurement. So let's take a look at what we see in the measurement screen. So this is the default screen layout in the new 2.50 software for both 3D phase and 3D stereo. We have the 2D image shown on the left side of the screen, and this is where we would place and position our measurement cursors. And we have the 3D point cloud view on the right side of the screen. So in the point cloud, we show this computed 3D surface data. And with that, we add spheres and lines that show you where your measurement cursors are placed on that 3D surface. And this blue outline is telling us where our depth measurement reference plane is located in 3D space. Now, if I want to see a full screen view of either the 2D image or the point cloud, I can just come down to the Views soft key and bring up the Views menu and select whichever view I'd like. So for this demonstration, we're going to stick with the split view. So now let's take a look at the point cloud of this particular measurement. So when we rotate this point cloud, it becomes immediately obvious that we're actually measuring on a very curved surface, which we didn't really notice looking at this 2D image. And this depth measurement that we're making is really measuring this curvature much more than it's measuring the depth of this indication. So we can tell clearly that this is not going to be an accurate measurement. So the first common mistake that's easy to avoid using the point cloud is misinterpretation of the shape of the surface. So another very common mistake that's made is performing small depth measurements from too far away. Now, why is this such a problem? We talked earlier about how stereo measurement uses this point matching process to identify common surface points in the left and right images, and then it uses that horizontal spacing to calculate the 3D coordinates. Now, this matching process works pretty darn well, but it isn't perfect. There's always some level of small error in this selected match position. And because the horizontal spacing is used to calculate the 3D coordinate, that match error creates some level of computed 3D error. Now, this matching error varies from image to image and pixel to pixel. And that variation will cause variations in your measured result. So this graph is basically telling us that for a given amount of matching error, the Z error that is caused by that matching error increases as the tip-to-target distance increases. So if I were to measure a certain feature a bunch of times out at 1 inch and repeat those measurements again down here at around 3/10 of an inch, what you'd see is that the variation in the results at 1 inch would be something like 10 times larger than the variation you would get in closer at 3/10 of an inch. So if, for example, the variation we see at 1 inch is in the 10,000ths of an inch range, and we're making a 1 inch long crack measurement, we're probably not going to worry about that kind of variation. But if we're making a measurement on a 10,000ths deep pit, and we have 10,000ths of variation in our measurements, then we can have a real problem. So when you're making small measurements, and especially small depth measurements, you want to be operating at this end of the curve and not up here at this end. And this is really true for first-generation stereo, 3D stereo, 3D phase, and even measurements on another manufacturer's scope. So the difference really is that we can see this variation easily using a point cloud, but it's really difficult to see when using just a 2D image. So let's look at some examples. Here we have a stereo image of a surface indication that looks like it might be a scrape or a groove, and we want to know the depth of this indication to determine if it might affect the integrity of this component. So here a depth profile measurement has been used, which is giving us a result of 0.004 of an inch. So just looking at this 2D image, the measurement appears to be performed properly, but there's really not much we can say about the accuracy of this 0.004 result. So let's take a look in the measurement screen. So the first thing you'll probably notice is this flashing orange outline around the MTD number. MTD stands for max target distance, which is the distance from the measurement tip to the furthest cursor location on the surface. So it's essentially the x-axis variable in that previous graph that we showed. Now, the Mentor Visual IQ includes a dynamic advisory system that looks at the type of measurement you're performing and the measured result along with the MTD. And in this case, it's saying, hey, you're making a small depth measurement at a fairly high MTD, which puts us up in that range on that chart where I said we didn't really want to be for these small depth measurements, because the variation that we would get at that distance is significant relative to this measurement result. So if I place, say, a point-to-line measurement, looking at the width of this indication, I don't get any orange outline and no messages because this type of measurement at this size is not likely to be severely affected by variation at this distance. So this is primarily an issue with small depth measurements. So we talked about how the matching error varies from pixel to pixel in the image. And that variation causes bumps in the computed 3D surface coordinates. So if we look at this point cloud, we would generally expect the areas outside of the indication to be fairly smooth just based on the 2D image. But what we see in the point cloud view is that those areas are sort of bumpy looking. So this is the noise I'm talking about that's created from this variation in this matching error. When I turn on the depth map, what we'd really like to see here is a clear signature of the indication and very little noise showing up in the areas outside of the indication. But in this case, we don't have that. The indication is not clearly defined, and we have all these bumps that are similar in depth to our indication area. So this is really our signal that we're measuring from too far away, and these bumps are likely degrading the accuracy of our measurement. So in this case, we would want to get closer and try this measurement again. So let's do that. So here's another image of the same indication taken from a closer distance. Now this time I'm going to apply the new area depth profile tool. And with that, we position two cursors on one side of the indication and a third cursor on the opposite side. And the software will search this region between these two reference lines and give us a depth profile through the deepest point in that area. And this works well on flat surfaces and even on curved surfaces, which we sort of have here. So now we have a result of 9 thousandths, so more than twice as deep as the measurement we had previously. And we're at an MTD of a little over half of the previous value. So when we take a look at this point cloud, we see that the areas away from the indication are quite smooth looking as we would expect. And we can clearly see the profile of this indication in the point cloud view. When we turn on the depth map, we see a nice clean signature of this indication showing up in this area, and the noise outside of the indication region is quite low. So this is really what we want to look for, or we want to see when we're making these small depth measurements. So, in summary, if you're making small measurements, especially of a depth type, you want to get as close to the target as possible, and you want to be sure to check your point cloud for noise bumps that might be degrading the accuracy of your result. So for our next example, let's go inside a gas turbine and take a look at a condition that's known as stator rock. So here we have a 3D phase measurement that's using a length to measure the offset between the platforms of these adjacent stators. We have a nice low MTD value of 379 thousandths, which we just learned is helpful in getting accurate measurements. So from this 2D image, this looks like it should be a good measurement. Now, when we go into the measurement screen and we take a look at the point cloud, we can immediately see that this length measurement is actually being made on a diagonal. So this is going to overstate the offset between these two platforms. So let's go over here and remove this length measurement, and we're going to apply a more appropriate depth measurement. So we'll set up our reference plane on this upper platform, and then we'll drop our fourth cursor down on the lower platform. So now when we take a look at our point cloud view, we can clearly see that we are making a perpendicular measurement of this offset between the two surfaces. And our measured result is now 30 thousandths, which is half of what we had with the length measurement.
Clark, this is just a really good example of what I was talking to earlier. The previous measurement may have kept this particular turbine offline for an additional amount of time, and that would have cost possibly hundreds of thousands of dollars in power, the ability to make power. So having that correct measurement is really important in this type of a case, and being able to use the point cloud to determine that is very helpful. So great example.
All right. Thanks, Tom. All right, so for our next example, we have another 3D phase measurement image, this time inside a riser pipe, where we have a surface indication that looks like it might be some form of pitting. So we have another depth measurement here, and what we'd really like to know is the maximum depth of this indication. So as we look at this 2D image, it's really hard to tell if that's what we've actually measured. So let's go back into the measurement screen, and I'm going to turn on the depth map for the point cloud here. And we can quickly see that the area over here in that indication appears to be deeper than where we're measuring over here. And if we take that point cloud and we rotate it around, we can confirm that that is, in fact, the case. So, seeing that, we can come back over to the left side and reposition this fourth cursor using the point cloud as our guide to get that measurement over to that deepest location. So while we can get here that way, that is kind of a tedious operation. So I'd like to show how a new feature in the 2.50 software that we call Depth Assist can help with that. So I'll remove the original depth measurement, and I'm just going to add a new one and place my first three cursors again on the main surface. But notice when I drop the third cursor, the fourth cursor automatically is dropped at the deepest point in this indication, which we can then verify using the point cloud. So in this example, with the 2D image, we had missed the deepest point, and we've shown how we can detect that easily with the point cloud and then correct it either manually or very quickly and easily using this new Depth Assist feature. So for the next example, we will move to aviation, where we're making a measurement of the tip clearance between the edge of a turbine blade and the shroud. So again, we're using a depth measurement with the reference cursors placed on the shroud and the fourth cursor placed on the edge of the blade, giving us a gap measurement of 31 thousandths. Again, looking at this 2D image, everything looks pretty good. see what we see in 3D. So as we rotate the point cloud, we quickly notice that our reference plane, which should be aligned with the shroud data, is actually tilted. And that's being caused by one of our cursors, which in 3D space, where the measurement is actually made, is sitting up here near the edge of the blade rather than down on the shroud where we would expect it to be. So I'm going to come over to the left image and reposition that cursor down to the shroud. And now we can see in the point cloud that our reference plane is nicely lined up with the shroud data, and we are getting a perpendicular measurement of this gap. And our result now is 61 thousandths. So we basically had a 50% error in this measurement. So this is another common mistake that can be made where a cursor may appear to be in a certain position based on the 2D image, but it's actually in a very different location in the 3D world where the measurement is performed. Now, before I move on, I wanted to talk momentarily about this green area that you've probably noticed in a few of these images. This is a new feature in the 2.50 software that we're calling surface mask. So what it does is it shows in green surface points that are very close to the reference plane for our depth type measurements. So if I reposition this cursor back to its original location, we see that we just have one little band of green on the shroud, and then we have a little band of green up on the blade. And we know that we want to use the shroud as the reference surface for this depth measurement. So this is a clue that we have a problem with the reference plane that we've established. When I move this cursor back down to the shroud surface, we can see that this entire area is showing up in green. So now we know that we have a good plane established. So the surface mask along with the point cloud are just two great tools for helping you avoid some of these common mistakes. And we talked earlier about how the depth assist feature can help you hit the deepest point in an indication quickly. And the depth assist can also help you perform these tip clearance measurements more quickly. So in this case, when I drop the third cursor on the shroud, the fourth cursor automatically appears at the edge of the blade. So this can be a really nice time saver for the users out there who perform a lot of these tip clearance measurements. All right, for our last example, we have another blade in a jet engine where the corner has been broken off. And here we'd like to know the area that is missing at this corner, which in this case is given as 57 ten-thousandths of a square inch. Now, to a non-expert, this might look like a legitimate measurement. But when we take a look at it in the 3D point cloud, we see that one of our measurement cursors is actually back here behind the blade down on the shroud, which, when we look back at the 2D image, happens to be exactly where we placed it. So those who are very familiar with 3D phase and 3D stereo may realize that you can't actually perform this measurement today because you can only place cursors on existing surface points. In this case, that surface we'd like to place the cursor on has been broken off, so we obviously can't put a cursor on it. Now, before I show how we fix that problem, Let me point out that we do have one cursor here that's shown in yellow, and there's a little yellow zone showing up in the image right next to it. So here the 3D phase processing is telling us that there's a region of data that may have reduced accuracy. And when we look at the point cloud view, we can see that there is a little bit of an artifact coming off the edge of the blade. So in this case, we want to take a look at our cursor position, and we can see that that artifact is not affecting the location of that cursor in 3D space. So we can go ahead and leave that where it is. So coming back to this area measurement, we have a new tool in the 2.50 software that we call a measurement plane. So I'm going to leave that area measurement in place and add a measurement plane to the image. So we'll place 3 of these triangular shaped cursors near the measurement area. And what this does is to define a mathematical 3D plane that effectively extends the surface of the blade out into 3D space over the entire image. The cursors of our area measurement are then projected onto that 3D plane. So that pulls this cursor that used to be back here on the shroud into the plane of the blade where the actual corner used to exist. So now we can actually do this area measurement. Now, when you use this combination of a measurement plane with an area measurement in this way, the software actually adds these lines in the 2D image that extend along the edges of the blade. So this helps us more accurately position this corner cursor so that we're well lined up with the original location of that missing corner. And we not only provide the missing area, but we're also giving you the length of these 2 missing edge regions, which some of the maintenance manuals will call out instead of the area itself. And we also give you the angle of this missing corner. Today we have a lot of blades that don't actually have right-angled corners. So using this approach, we get all the dimensions you might be interested in a single shot. We can do the measurements with 3D phase or 3D stereo, and we can give accurate results on blades that don't have right-angled corners. And we also, using the point cloud, we're able to identify a problem with our measurement that in this case was causing 150% error in that measurement result. So a pretty nice new feature in the 2.50 software. And with that, I'm going to turn it back over to Tom.
Wow, thanks, Clark. That was really great. So to summarize today, we talked about why accurate measurements are essential in critical RVI applications. That's why we measure. We discussed 3D phase and 3D stereo, the only 2 technologies available today that bring point cloud analysis to meet a variety of industry measurement needs. And most importantly, we've demonstrated how point cloud visualization helps inspectors make better decisions by avoiding common measurement pitfalls. And I said earlier how important that is in terms of uptime for our asset owners and safety for the folks that use those assets. With that, I hope you found today's presentation useful. I'd like to share some links now to some additional resources that are available online. The measurement handbook, Clark talked about that earlier, is free. It provides really a high level of detail on each of the measurement technologies we discussed today. It also points out what measurement types are best suited to solve different applications. So if you're unsure, it'll take you through that, and it'll even share best practices within these applications, many of the things Clark went over today in some of his examples. We have a free poster. It's a 3D measurement poster just available. So please download that, get a copy of that for yourself, put it up in your shops or wherever it is you do your work. And then visit our measurement webpage. You can learn a lot more about measurement in our GE video borescopes. We have GE video borescopes of different lengths and diameters, really to solve almost all the applications that you'll encounter today doing inspections. We also offer inspection courses through our Measurement Academy, our Inspection Academy, measurement in this case, and they can be done online or in the classroom. And lastly, if you want a live demonstration, just reach out to your local representative and schedule an appointment. We really love to get directly involved with your applications and help you solve those specific problems that you have. So please reach out if that's interesting to you. And now we really want to hear from you. So if there's any questions out there that have come in, or if you have questions that you've been waiting to answer, now's the time to do that. I'll turn it back over to the moderator of the call.
If you'd like to ask a question at this time, please press star 1 on your telephone keypad.
I would tell you there were...
Again, that is star 1 if you'd like to ask a question. Your first question comes from the line of Dave Mill. Your line is open.
Yes, I saw that it looks like it's pretty accurate for measuring depths. Is this also good for measuring heights for small protrusions?
Sure. Yeah, we have, the depth measurement type, the depth profile, and the area depth profile. Those can all be used to measure heights as well as depths. So even though the name would imply depths, they aren't limited to negative going surface contours.
Okay, great. And on the demonstration, I saw the image manipulation seemed pretty easy. Was that being done when the image is downloaded to a computer, or was that being done? Is it a little more difficult to do those manipulations on the handheld device itself?
Yeah, it's really a great question. Well, what Clark had said earlier is he was doing it on a PC using a mouse, but with our actual video borescope, we have a touchscreen interface, and it actually works very, very nicely, as you might imagine, using a touchscreen.
Okay, great. And one last question, calibration. Is this a self-calibrating device, or what can you tell me about that?
Yeah, another great question. So when these video borescopes leave our facility, so after you've ordered one and we're shipping it to you, the tip optics that are going to do the measurement have been very precisely calibrated to the device. When you receive it, you will also receive what we call a verification block. This block is traceable to the NIST standards, and so what we recommend is each time before you do a measurement and then after you're done with that measuring that day, you test it within that verification block and to make sure that it's measuring precisely. And that's really all you need to do. Whenever you send it in to us for any reason, we would also check the calibration in the factory.
Excellent. Thank you very much.
You're welcome.
That's all I have.
Your next question comes from the line of Michael Frieda. Your line is open.
Thank you. Just a quick question. Would this be available with UV light or fluorescent penetrant indication measurements?
Yes, we do have that available as a custom product, and I will let Tom maybe tell you a little bit more about that offering.
So almost two answers to that one question. The first is we have video borescopes where we are able to drive UV power through the fiber bundle to transmit that power into the application. So we have that, and we can help you with that. From a measuring standpoint, which I think is what you're asking, we would be able to do that with the 3D stereo measurement that you saw today. the 3D phase measurement wouldn't be able to do that today. So yes, it's available in our 3D measurement software with our video borescopes.
Thank you.
Your next question comes from the line of Alex Prizzi. Your line is open.
Hi, yeah, I have some concerns about the accuracy of the measurements you're getting. Because it looked like earlier when you're showing some variation depending on how far away from the subject matter the camera was. So as you got closer, your resolution got better, and it seems like your measurement data became more accurate. How do you know when you're in that sweet spot, so to say, that you're close enough that it's correct?
So as we discussed in that section, this is primarily a concern when you're making very small measurements. And in those cases, if you want to get the best results, you really need to get as close as you can to the surface. And again, the 3D point cloud view is sort of your best tool to assess the accuracy that you're likely to be getting. And you want to look for low noise in the areas outside of the indication and a clear signature of that feature. And we do, incidentally, have some accuracy curves. If you download that 3D measurement handbook that we mentioned, we have curves in there for 3D phase measurement at the end of the handbook. So that'll give you some idea of the capabilities of the device.
Okay. If I could ask, what are you measuring, and what kind of sizes are you talking about?
We're kind of the thing that I'm looking at right now are pits and welds, somewhere in the neighborhood of like 15, 30 thou.
Yeah, so I think we'd be happy to even come out and do a demonstration for you. I think you'd be very satisfied. We can test it against knowns, but that particular size that you're talking about is very much in the sweet spot of what we can do, assuming you can get close enough to it, which with our video borescope products, you need to be somewhere around an inch or closer. And the smaller the defect is, the closer you'd want to be, as Clark had demonstrated.
Okay.
Hey, if I can, this is Paul Thompson. There's one additional piece I'd like to add to it because your question is spot on. You just don't know when you're using some measurement types if you're in that sweet spot. And that's especially true for your traditional stereo, which it is a 3D measuring system, but it's only at the point of reference where you're measuring. You don't get the point cloud. And so until you have that point cloud to look at the health of the information which you're actually using, you just won't know if you're getting good measurement data or not unless you do many measurements, take a lot of time, look at the variation of how much of the measurement value is changing with each pixel measurement. And so what Clark and the team have done is taken a lot of that guesswork out of there with the dynamic advisory messages. So if you're trying to measure an indication whose size is smaller than the tip to target distance would allow for precision and accuracy, you're going to have a dynamic advisory message that Clark showed you earlier, flashing in orange around the measurement value.
Okay.
Thanks. Good question.
Your next question comes from the line of Nathan Jewell. Your line is open.
Hi, how you doing? I currently use one of these, and we're having a bit of a problem with highly reflective surfaces on stainless steel inside a pipe. Is there a good remedy for that?
Yeah, so those highly reflective surfaces can be a bit of a challenge. Are you using 3D stereo or 3D phase in that application?
I'm sorry, 3D phase.
Okay. So with 3D phase on these reflective surfaces, you do want to view them from a non-perpendicular viewing perspective. So if you look at them at an angle, you tend to get significantly better 3D data, which you can check in the point cloud view. It may be also worth trying 3D stereo at some point, which sometimes will give you a little better performance in those highly reflective applications. But again, with that, with stereo, the thing that gives you the most trouble is glare in the image, which again can happen with a perpendicular viewing perspective. So off perpendicular views tend to help you with both technologies.
Okay. One more question, which kind of leads into that. The angle of approach to some pits and maybe some like weld reinforcement. What are you guys finding is maybe a sweet spot for the angle of approach sometimes? Is it 10, 15 degrees or 25? Or does it just really depend on the surface overall?
So it does kind of depend on the surface, but in general, on those shiny surfaces, you might even go as far as 40, 50, maybe even 60 degrees off perpendicular to get your best results. So you can go quite far off perpendicular.
Okay, thank you.
Yeah, and I'll just add a comment. It may be obvious, but with these measurement technologies, you can buy measurement tips that are 90 degrees or straight on. So you could mess around with either of those depending on how you're getting into that particular area to look at it, to be able to nicely change those angles we've been discussing.
Again, if you would like to ask a question, please press star 1.
So there is a call on the chat window, and the question is from Jose: how do I close a space for an area measurement?
So when you're performing an area measurement, after you've placed 3 or more cursors on the screen, one of the soft keys will be labeled with a done label. So you would press that soft key or the associated hard key, which will then close off that area measurement.
Pardon me, your next question, it comes from the line of Brian Sung. Your line is open.
Hello, I'd like to ask you the minimum angle for taking this depth profile, because one of my customers are using 3D for their pit measurement, but the pipe is so tight that you have to just use the orange tip for this measurement, and they want to know the minimum angle that they could take the depth profile.
So there really isn't an angle limitation as long as you are seeing and getting 3D data all the way down into the bottom of the feature. Now, when you're measuring on a curved surface, you do have to be careful with depth profile about how you're positioning your cursors. So you want them to be spaced longitudinally down the pipe versus across the pipe, which would include the curvature of the pipe and the actual measurements. And area depth profile would probably be a very interesting measurement type for those applications. So it's really designed to work well on both flat surfaces and curved surfaces. And you don't have to worry quite as much about cursor placement, because there are smarts built into that measurement type that help you ensure that your measurements are made in the longitudinal direction along the pipe. So I'd suggest taking a look at that new type.
Yeah, and just to refresh, that measurement type, area depth measurement that Clark's referring to, will soon be available with our new 2.50 software as an a la carte feature to the Mentor Visual IQ, and that'll be released shortly within the next week or so.
I have one more question. Will it be available for XLG3 3D PM?
So XLG3, our previous platform for our video borescoping and measurement software has been retired, and so we won't be building software out onto that platform anymore. We'll be moving on to the IQ platform.
Okay. Thank you.
You're welcome.
Your next question comes from the line of Alex Prissy. Your line is open.
Yeah, guys, I had a couple other questions. So one is, do you have any sort of videos available at any of these links here that you currently have up on the screen that I could show to someone else on our team to see if this suits your needs? And also I had a question about, you had talked about making sure that if you're looking at 3D curved surface, will it account for if you have a convex surface that's also on an inside diameter? I mean, do you have to have one flat plane, or can it account for multiple curves?
So let me answer that last question first.
Okay.
If you're asking about the area depth profile measurement,
Yes.
It's really intended for use on surfaces that are flat or have curvature in one direction, such as a pipe. So if you have a complex curve going in multiple directions, that curvature would contribute to the measured result in that situation. So you may be better off using a depth measurement and being very aware of how you're placing the cursors and how that is affecting the measured result.
Okay.
And with respect to videos,
Yeah, so with respect to that first question, this particular webinar has been, there's audio associated with it, so you could have that and go through that with your whoever would like to see this. I'm happy to share that. And then further to that, if there's a particular discussion that you want to have or you'd like one of us to be involved, we'd be more than happy to take someone through this, talking specifically about the applications and problems they're trying to solve.
Okay. Yeah, we have another group across town here that does some analytics on failures and teardowns, which I think this might be applicable. So.
Okay, yeah, and I believe this entire webinar will be recorded and made available through a follow-up email after this is completed.
All right, thank you.
Okay.
There are no further questions at this time.
Well, thanks, everyone. Paul, did we have any more coming in through chat?
On the chat.
So I think it's been really good to hear the questions come through. I really appreciate and helps us. So thanks, everybody, for coming on board today. We really enjoyed showing this to you. Please reach out for these additional resources and get a copy of this whole presentation and share it with whoever you might think might benefit from it. Thanks again.